Okay, we're going to introduce one of the three most important concepts in vector calculus for the purposes of this course, and that is Green's theorem. So everything we've learned in the course so far, we've learned parameterization of curves, we've learned line integration, we've talked about conservative fields, we've talked about closed loop integration, then we talked about double integrals surrounded by curves. So all those things come together in Green's theorem, and this is the reason we've been doing all of those things as we've gone. So Green's theorem is actually a 2D case. It's sometimes called Green's theorem in the plane, and it's going to apply to functions over x and y. And later on, we're going to generalize this. It has a different name when it's generalized. It starts to become Stokes' theorem, but right now it's important enough to have its own name, Green's theorem. And what Green's theorem says is if we have a curve C, okay, like we've had many times before, okay, we have some curve C, and we've got a positive orientation in it as we go around here clockwise. So as you walk around, the inside of the curve is to your left. So if that curve is a piecewise smooth, simple curve, so it doesn't have to be smooth, it can be segmented, but it's going to be piecewise, and then every piece has to be smooth. And smooth doesn't mean curvy, it just means it doesn't have corners. C is piecewise smooth. It's a simple curve, and it's bounding a simply connected region R. So a simply connected region doesn't have a pinch point in it. But so this is a pretty typical picture of it. If over that region R, these functions p, q, the partial of p with respect to y, and the partial of q with respect to x, what p, q, and these partials are, we'll say in 1 second. Okay, but if these functions are continuous on R, so they're well behaved on R, then this is the relationship we have. This is the Green's theorem. That the line integral, it looks like f dot dr, right? If f as a vector field is pi plus qj, and we dot that onto dr, like we were going to calculate work or something to that effect. So p is the x component of the vector field, q is the y component of the vector field. So if you form the closed contour integral of f dot dr, that will equal the double integral over the region R, which is enclosed by C. But now it's the double integral not of p and q, but it's the double integral of the partial of the y part of the vector field with respect to x minus the partial of the x component of the vector field with respect to y, dA, right? So we have the contour integral of C, and we can convert that into a 2D integral over R. And many times we're going to see that's easier to do. It also is powerful in terms of what it gives us in terms of stating, for example, law like Maxwell's equations and things like that. These rules we'll use them there. Okay. So that's the statement of Green's theorem. And what I'm going to do here, this is a pretty short module introducing it. It's as simple as that. I'm just going to do one example using Green's theorem, calculating the double integral, and then in the notes we have, and the notes I'm going on are Green's theorem part 1. It actually does that same integral the old way as the contour and shows that they're the same. And we're not going to go through all that here. We're just going to actually apply Green's theorem directly. Okay, so here's the example. Let's get this. The example that we're going to do is I'm going to let f be a vector field. We're going to say x squared minus y squared I plus 2y minus x j. That's my two-dimensional vector field. I want this for C bounded by these two curves. Y, this is x, this is 1, 1, and we're going to have x squared. This here is y equals x cubed. On top is y equals x squared. At first glance, you might say, wait a minute, x cubed is always bigger than x squared. Well, it's not true if x is less than 1. Okay? So above x1, then that will overtake that 1. This is approximately a drawing of it. It's not a perfect drawing of it. I'm going to go up y equals x cubed to 1, then come down and go the other way. This is piecewise smooth. Okay? It's got corners to it, but over this region it's smooth, and it's connected right here, and then over this line it's smooth. So that applies. Okay? So, this is what we're going to do. And we're going to use Green's theorem and say, okay, well, if this is R, the region contained there, this thing is going to be equal to this, and I'll show this in a moment. Okay. So, making our identification, so we're saying, well, P equals x squared minus y squared. And then I need the partial of P with respect to y, which is minus 2y. And then I have Q equals 2y minus x. And then I need the partial of Q with respect to x. Where I remember this is the x part of f, I need the partial with y. The y part of f, I need the partial with x. So partial with respect to x is minus 1. Okay. So here, like I wrote was, the partial with respect to q, so minus 1. And then I have minus of the partial with respect to p with respect to y. Okay. So really what we're integrating then, the problem becomes calculating this contour integral, which is going up here and then down here, is really the same as doing this as r for 2y minus 1 dA. Okay. Okay. So now, I mean, already in this course, we would start with this problem. So there's nothing new in Green's theorem in terms of execution. The only thing new in Green's theorem is the realization that a contour integral can be equal to a double integral over a region enclosed by the contour under certain circumstances. And they're pretty broad, right? The only rule is that these functions here, the functions here, this component and this component, need to be defined in R. There's no trouble there. Continuous. And the partial derivatives need to be defined in R, and there's no trouble there. So this is a pretty general thing. Okay? So now I'm just going to execute this integral. So doing this integral, right, like usual, we just have to figure out our limits of integration. I'm going to integrate over y first to get rid of the x's. Get rid of y in favor of x, and then we'll finish off with x. So x goes from 0 to 1, right? Because this is the limit 1 here, starts at 0, and y goes always from x cubed to x squared. Think about what's y over this region R. What is, you think about a variation in y, what's y bounded by? It always goes from the bottom function up to the top function. Okay, so from x cubed to x squared. So this would become x cubed to x squared, and then I have 2y minus 1. Okay, dy dx. I'm going to do y first. Okay, so this thing becomes, I'd have 0 to 1, and then we'd have 2y squared over 2, so y squared minus y from x squared to x cubed. I'm going to have dx when this is done. So this becomes kind of a polynomial, not kind of a polynomial, it will be a polynomial. You put x squared, so this becomes x to the 4 minus x squared, there, okay, minus then x cubed here, so this becomes x to the 6th minus x cubed dx. I just did that to make sure I keep track of this minus sign correctly. So you could write at this stage, I would write it, I tend to go really slow when I do these things. 0 to 1, x4 minus x squared minus x6 plus x cubed. I was looking to see if any of the polynomials add to each other, but I got 2, 3, 4, 6, so there's nothing to do there. dx. Okay, well that's pretty easy to do. Let's just go through here. I'll just squeeze it in to this section here. So this thing becomes, if I do those, that's like x to the 5th over 5 minus x cubed over 3 minus x to the 7 over 7 plus x to the 4 over 4, 1 to 0. Now the zeros, they're all going to be 0, so I just got to put 1 in here. So this becomes 1 over 5 minus 1 over 3 minus 1 over 7 plus 1 over 4. Okay. And let's take the two negatives and so put the two positives together, 1/5 and 1/4, so that becomes 4 plus 5 over 20 minus 7 plus 3 over 21. Okay. So that's like that, right? So this would become 9 over 20, so we have basically 9 over 20 minus 11 over 21. So this thing becomes 9 times 21 minus 20 times 11 divided by 20 times 21, and that thing equals, what do we got here? Minus 11 over 420. Okay. So whatever, it's a number, but that's our simple result by doing this area integral. If you do, and in the notes we do this, if you go through and actually do it the other way, the contour way, so I go along the first contour, do the line integral, then I do along the second contour, goes up, you get the same answer. Okay. In this problem, you know, this integral is pretty easy, the contour integral is pretty easy, so they're all pretty easy. And it may not make a lot of sense to, like, why do we care about Green's theorem? This just replaces an easy thing with an easy thing. But what's going to happen, and we'll show you in the next module, and they're kind of contrived, but you can create problems or see problems where it is all but impossible to do the contour integral, but the double integral is very easy. And that is often the case. Often this is hard and this is easier. And that's what we use Green's theorem to do. We almost think of Green's theorem as a way to compute closed contour integrals. It's not just that. There are times, and I can create problems where this side's really hard and this is really easy. And that, okay, that's cool too, right? It's just a tool, one versus the other, right? Now, there's one last point I want to make about this, and this is kind of looking towards Stokes' theorem a little bit. But I want to, let me just go back to where we were before and just rewrite Green's theorem in general and just make a couple observations about it. Okay? And then afterwards we'll just do more problems with it. But again, the problems that we're doing with Green's theorem are just like the problems we've already been doing. They're just double integrals or contour integrals or both, right? So there's nothing new. One thing I would say, well, this is kind of the next module, but you can use polar coordinates. Green's theorem is true no matter what coordinate system you're using. So let's just mention Green's theorem again. Okay, so we said this. Okay, closed thing C plus P dx plus Q dy, right? And we say that's R, where R is enclosed by C of di Q di x minus di P di y. Okay. Now, two things. First thing, so our requirements on the functions here, were nothing like, if we say f equals pi plus qj. Does f need to be conservative for Green's theorem to be true? No, not at all. And in fact, right, if f was conservative, Green's theorem is trivial because, remember, if f is conservative, then the integral of f for any closed contour is 0 because f is independent of path. And the other thing, but the more typical test was, well, also then the curl of f needed to be 0. And this is the second point we want to make. Okay? So first point is, does f need to be conservative? No, not at all. Remember there was a test, so we said that the test for f being conservative was that the curl be 0. But when we were just doing in 2D, I said, well, but really the curl being 0 in 2D is just saying that the partial of the y part component with respect to x equals the negative of this. So just remember, right? So let's remind ourselves one thing, what that curl looks like. The curl of f for graph given here. F, right? I, J, K, partial X, partial Y, partial Z, and then we have P, Q, 0, right? Because I'm doing it for this function F, which has no Z component and no Z variation in it. Then, okay, so this is 0I minus 0J, because the I component, you take the partial of 0, and the Z dependency of Q, which is 0. You take the partial X with 0, 0, and the Z dependence of P, 0, okay? But then we have the K part, I got, well, die Q, die X, minus die P, die Y. So actually, this thing here, if I write it like this, I could write as right? Dot f dot dr on a closed contour is actually equal to the perpendicular component of the curl of f integrated over the area enclosed by C. Okay? And that's why this idea of this f being conserved, if f is conserved, the curl is 0, this is 0, this is 0, all zeros, it all makes sense. It's all consistent, it's kind of trivial. But the idea that Green's theorem is relating a contour, okay, in 2D space to the perpendicular component of the vector field integrated over that area, that will be extended and expanded into 3 space when we get to Stokes' theorem. To do that, we're going to have to learn how to do surface integration, and that's the next thing after Green's theorem. Okay? So now for the rest of this section, we'll do a couple other examples of Green's theorem. Again, most of them they're just straightforward, either doing contour integrals or doing double integrals. But we'll highlight one funky thing in which we can we'll identify cases where Green's theorem doesn't work, where there's singularities, and then we'll use Green's theorem to convert a closed integral to a different closed integral, a hard one into an easier one, and that'll be kind of a trick, and that's one of the things we'll talk about in the next module.